Hey everyone, welcome back to the channel. So in today's video, we are going to discuss about consistency models. So this is our second video on our second section. So we are discussing about this. So we have already covered our introductory sections and we have already covered cap theorems also in our playlist. So this is the second video on the section number 2 of fundamental of distributed systems in our RGB system design playlist. So let's start with that. So instead of using jargons and all, we'll use consistency models with real life examples so that you can easily relate to it. Okay. So we'll cover three main types of consistency, that is the strong consistency, eventual consistency, and casual consistency. So stick around till the end. First, before starting forward, let's just understand what do we mean by consistency models and what do we mean by consistency first in distributed systems. So imagine you are using different devices to access an app. Let's say you are using Grow or Kite for your trading needs. In that case, you expect the same information on both at the same time. Or let's say you are doing any transaction, you are viewing your bank statement in your phone also and in your laptop also. In parallel, you have done a payment using your phone. Ideally, what you expect the information shown on all the devices on that application should be same, right? But it depends on how the system is built and what is the requirement of the system. I mean, ideally the data stored across all the devices should be consistent, but there are three types of consistency models. I mean, how the data will be updated. Based on that, we have three types of consistency models here. We have the first one is strong, eventual, and casual consistency. So let me just go to the first slide, that is for strong consistency. For strong consistency, just think about an ATM machine. When you withdraw money from it, or let's say you are using a UPI app like PhonePe or Google Pay or Credit. So when you withdraw money or transfer money to your friends, and you notice that immediately your balance is updated across all the bank servers. I mean, with this example, you must have understood why do we need strong consistency. So strong consistency we need where every read request need to reflect the most recent write. I mean the most recent write that we have done. Let's say we did a write operation to update the bank balance in your account. That is a write operation, and that needs to be displayed across all the devices. So that is the first requirement of implementing or deploying strong consistency. The next reason we need strong consistency is we do not want to have outdated data. In that cases, we need strong consistency to be implemented. And where do you implement strong consistency? It is usually implemented in financial systems like UPI apps, bank servers, right? So that was about strong consistency, and let's discuss how do you implement strong consistency. So in order to implement strong consistency, you can use a distributed consensus algorithm. We are going to discuss about consensus algorithm in details in our upcoming videos, all right? But let me just give you a gist now, okay? So using distributed consensus algorithms like Paxos or RAPT, you can ensure that all copies of the data remain synchronized. Like let's say you have two servers. Let's say we have multiple servers, right? Multiple database servers, for example. All right. Let's say this is our database server, and we have replications, right? Let's say the HDFC Bank uses replication to store the data across multiple servers of its customer. So using this distributed consensus algorithm, we can ensure that the copy of the data, I mean, if a balance is updated here, the same should be updated across all the servers in a synchronized manner. The Paxos is actually a consensus algorithm. By consensus, what do you mean? That before writing or before committing any write to a particular database or updating the data in a particular database instance, all of the servers must agree on something. It's like a group vote where you vote for something, where all servers must agree on the latest update or latest changes before proceeding, right? So it's kind of a voting that, yeah, the balance update is a correct operation to do, and let's perform that. The next technique to implement strong consistency is to do synchronous replication. Once update is approved using the consensus algorithm, the data that is written, right? Every update must be confirmed by all the servers before being shown to users. I mean, we have to ensure that all the database nodes, or all the server nodes are up to date with the latest data before, I mean, start serving the user request. You understood, right? For example, here you updated my bank balance as let's say 100 rupees, but that update was not propagated, and here it was still 120 rupees. So if I open my phone app in my phone, and the request goes to this database node, then it will show 120 rupees, right? But मैंने तो 20 रुपये डिडक्ट मतलब withdraw कर दिया था already. So that's why before serving the user request, it is quite important to ensure that all the database state are up to date. right? Now, third step in order in implementing strong consistency is implementing global lock. What do you mean by global lock? Now, using global lock, we can prevent changes from conflicting by making sure that only one update happens at a time. Okay, it's like a single person holding the key to open a particular box and make the changes and then lock it. So using global locks, it is important because at the same time, if there is inconsistent writes done to this database, or unwanted balance can be shown, or erroneous balance can be shown in the application. So that's why it's important to include global locks in the application. Alright, so these are the three steps that we need to think about when we are planning for strong consistency. So if your application needs strong consistency to be implemented, you need to think in this direction. Benefit of this is it guarantees accurate data, right? And we are ensuring that the data is updated across all servers. So it is ensured that you will get updated data. But there is one trade-off. It is slow and expensive because we're waiting for the data to be propagated across all the instance, right? Then we are, allowing the user request to be served. So this is kind of a slow and expensive operation. That's why it is implemented only where it is required. That was about strong consistency. Now let's just move to the second thing. Okay, it's about eventual consistency. You all use Instagram, Facebook, etc. Right? When you update your profile picture in Instagram, let's say you opened your phone app, you updated your profile picture in the Instagram app. Now, if you open your account in your friend's phone or your laptop, profile picture update is not immediately visible to you. So somewhere caching plays a role. Along with the caching, I mean local caching that has been done, there is a eventual consistency implementation takes place in which the update that we have done, it is not updated instantly across all the servers. Why do we need eventual consistency, and how does it work actually? So eventual consistency works on async writes, where synchronous writing is not that much of a necessity. With eventual consistency, data lag does not bother you. The profile picture, if it is the updated image is shown across all the devices, let's say after 2 minutes, it doesn't bother the user that much, right? So at any given moment, different devices might show different versions of the data. It's not only about the devices basically. If I portray it this way, let's say there are multiple servers, right? It's finally boils down to the servers actually. It's not directly about the devices. Let's say we have multiple servers and we have opened our Instagram profile with your laptop. Let's assume that the request, the request from your laptop goes to this server and request from your phone goes to this server. So if the profile picture you updated here, right? Let's say that updated the data in this server, your image data, right? But that image update data was not propagated to this server because this is a server cluster, right? These are the replica of each other, let's say. So these are the replica servers, right? If the update from this server is not propagated to this server, the profile in your laptop will show the outdated image. So this is where data lag happens, but it does not bother the user. So given enough time, eventually the servers will synchronize, and all the requests that are being sent to these servers will show the updated data. So where eventual syncing is acceptable, we can opt for eventual consistency. But eventual consistency cannot be used for bank application, right? You understand why. Now, how do you implement eventual consistency? In order to implement eventual consistency, you can go for asynchronous replication. Asynchronous replication is just the opposite of synchronous replication. Okay, asynchronous replication means just like here we are doing synchronous replication, right? In strong consistency, where the data has to be updated across all the servers in a synchronous manner. Then only user request will be served. But in asynchronous replication, as I told, the image can be updated here, and gradually in asynchronous manner, the same image can be propagated to other servers also. The updates are done in the background, and which allows the system to stay responsive even if the copy of your data is not propagated to other servers. The core difference is with synchronous replication, your entire server cluster becomes unavailable to accept user requests till the point all the servers are up to date with the latest data. But in asynchronous replication, still this server is able to accept request from this laptop and serve the request even if the updates is going on this server. That's how the asynchronous replication works. The next thing is you can implement something called gossip protocols. So gossip protocols basically work like a rumor spreading system. When you spread a rumor, it spreads like fire, right? In a gossip protocol, it's basically servers gradually share the updates with one another until everyone is up to date. So this will, let's say, share the update to this will share the update to this. The next thing we can employ is the CRDT, which is conflict-free replicated data types. So using CRDTs basically allow the data to merge correctly even if updates happen in different places at different times. Like let's say when two people are writing on a single Google Doc, in the same line, if two people make changes, right, it ensures that the changes are merged perfectly. So that's how the CRDTs ensure eventual consistency. Even if writes are being done at two places, it still smartly handles that merge process and shows the updated data. What is the trade-off? As you can see, your system remains available all the time, even if there is a write going on in one of the server instance. So it's definitely faster than strong consistency, because updates don't need to be immediately propagated to all the servers everywhere and blocking the servers. No. But the trade-off is that temporary inconsistency might occur, just like I told. I mean, in phone you have latest profile picture, but in laptop you don't have in your Instagram profile. But that is quite acceptable, right? That's in those use cases we basically go for eventual consistency. So in social media platforms like Twitter ho gaya, aapka Facebook, Instagram, we use eventual consistency. They use eventual consistency. And large scale cloud storage like Dropbox, Google Drive, Amazon S3, वहाँ सब में भी asynchronous eventual consistency is employed. Now let's move on to the third type of consistency model, which is the casual consistency. So think about WhatsApp messaging. Let's take a WhatsApp messaging case where if you send a message to your friend and your friend replies, so it makes sense that their reply should only occur after your message, right? You sent a message, then they replied. So if the reply comes before your message, doesn't make sense, right? The order that we saw, that the order matters here. So that's where the casual consistency kicks in. What do you mean? I mean, what do you mean by this? How the casual consistency works and why do you need it? So where sequence matters for you, right? That means you want to ensure that the related events, that means I messaged my friend, he replied. These are events. So these two events happen in the correct sequence, not the other way around. Where unrelated events may appear out of order. When there is a need for collaborative applications, like in Google Docs, you want live collaboration, you want to play a multiplayer game, right? Or in chat application like my WhatsApp, Messenger, etc. So in those cases, we need to think about casual consistency. Now, let's say we think about casual consistency, right? Now, how do you implement that? In order to implement casual consistency, you can first what you can do is to use the vector clocks. Now, what is a vector clock? There is a term called clock. Clock is about time, right? So vector clocks basically help you track the sequence of updates or events, so that the dependent events, I mean messaging, then reply, message, reply. So those dependent events happen in the correct order. So it's basically, you can just imagine it like, a timestamp against each event that records when that event happened relative to other events, so that you can, order them one by one based on the timestamp. So it's not that simpler, but vector clocks का जो core है, the core flavor is around that only. Maybe we'll discuss about vector clocks in detail in some other video. So the next thing is to go for dependency tracking. Now, dependency tracking basically ensures that if one event depends on another, so it won't be shown to the user until the first event has happened. In order to implement casual consistency, we can define the dependencies. For example, let's say we have two tasks to do, task A and task B. So until and unless task A is completed, task B won't be marked as completed. So task A has to be done before we do the task B or go for task B. I mean, we'll discuss gradually in our upcoming videos how to implement this in detail. But right now, I'm just giving you an overview of these things. So there are some DBs which support casual consistency out of the box, like you can go for Amazon DynamoDB. Then Antidote DB is there. So a lot of DBs are there. CRDT based databases are there. They use this kind of techniques to maintain the order of the events. The benefit of using casual consistency is it maintains the logical sequence of events, definitely, as you discussed. But it's quite complex to implement. We'll be needing a separate video to discuss about these things, like how do you implement this. And that's a wrap about the consistency models that we have in system design. So these models define how distributed systems handle data updates in real life. A particular distributed system can go for strong consistency for instant updates, eventual consistency for gradual eventual updates. So it depends on the application requirement, and accordingly you need to think about the consistency model that you want to choose for your system design or the distributed systems at hand. So if you found this video helpful, don't forget to like the video. Let's target for 40 likes to this video, and we'll be covering all the topics all in a section wise manner, in a one by one hierarchical and proper structured manner, so that you will understand all the concepts of system design with examples, and with the best lucid way possible I'll try to explain. So keep an eye on this RGB system design playlist in my channel. All right, so yeah, if you like this video, don't forget to subscribe to my channel. We are targeting to reach 3000 subscribers by the end of this month, so keep supporting. So if you have any discussions or any doubts about whatever we discussed in this video, drop them in the comment section. I'll be sure to answer them. Okay. So thank you for watching this video, and I'll see you in the next one. Thank you.